We have seen yesterday, I will remind you, how do we implement the hybrid Monte Carlo algorithm on the example of a scalar field theory, which we have discretized and written in Euclidean spacetime on a discrete lattice. So let me briefly remind you of the steps that we've introduced for the hybrid Monte Carlo algorithm. At the beginning of today's lecture, we are going to go in a little bit more detail in each of these steps, since we had a lively discussion towards the end of last lecture, and then we'll move on towards discretizing quantum chromodynamics on the lattice. So the first step in HMC, as we've seen yesterday, was the momentum heat bath algorithm, which generates a fresh set of these auxiliary variables which we've introduced in our hybrid Monte Carlo Hamiltonian, the momenta, which are distributed according to simple Gaussian distribution. Then we've seen that in the second step, we perform molecular dynamics evolution of the Hamiltonian equations of motion according to the Hamiltonian of the scalar field theory, which we've defined by utilizing these auxiliary variables added to the partition function. So the HMC momenta, and then plus the discretized Euclidean action of scalar field theories, which acts as a potential in the classical mechanics sense, if we consider this Hamiltonian. And then the third step was the acceptance-reject step, where we said after solving Hamiltonian equations of motion for certain periods of time of Monte Carlo time, which we've denoted as a trajectory in the phase space spanned by these two variables, momenta and our field variables, then finally our evolved fields after the Monte Carlo trajectory tau are either accepted or rejected as a new field configuration in our Markov chain. And this accept-reject step accepts new field configuration with the acceptance which is equal to the minimum of 1 and e to the minus delta h, where this delta h was defined as a difference between the final Hamiltonian at the end of the trajectory minus the Hamiltonian at the beginning of the Monte Carlo, of the hybrid Monte Carlo trajectory. So let's first discuss in a little bit more detail how is this momentum heat bath performed in practice. So how do we actually, starting from some uniformly distributed random numbers, obtain Gaussian distribution of the momenta? So we've said yesterday that each of the hybrid Monte Carlo trajectories starts by a fresh set of momenta. So they are independent of our original field variables. And we will use random numbers in order to generate these fresh momenta distributed according to the Gaussian distribution. And random numbers are in general an important topic in all Monte Carlo simulations, and we are not going to go into details in this lecture what one considers a good random number or sufficiently good random number generator in order to make sure that our simulations are correct. But I'm just gonna quote here a popular choice for a random number generator used in lattice gauge theories, but also in other fields of computational physics. So the name of this generator is RunLux, and this is yet another contribution of your next week's lecturer, Martin Lucher, to the computational physics. You can look up the details, and there is a code also, sample code available for this random number generator in the numerical recipes. So assuming that we have sufficiently good random number generators, which generates random numbers which are uniformly distributed in a certain range. So a random number usually gives you a uniform distribution, and you now need some procedure which will turn your uniformly distributed random numbers into the distribution that is required in your algorithm, in this case, this Gaussian distribution for the momenta. So random numbers are we will use random numbers uniformly distributed in the range 0, 1, so in the interval between 0 and 1. And then to obtain the normal distribution, we will apply the so-called Box-Müller procedure. I'm not sure if there is a umlaut here. So the Box-Müller procedure translates two random variables. So if you choose two random numbers in the interval 0, 1, and then so they are drawn according to the uniform distribution. And then if we perform a following transformation, so we define variable y1, which is equal to the square root of minus 2 logarithm of 1 minus x1 times cosine 2 pi 1 minus x2. And similarly, y2, which is the same as the above y1, but just has a sign here. So the normalization factor is the same, and then we have here sine of 2 pi 1 minus x2. Then it turns out that these yi variables are drawn according to our wanted normal distribution. And you can demonstrate this rather easily. It's just important to note that for numerical considerations, one actually takes here 1 minus x1, since we are working at the interval which includes 0 but doesn't include 1, such that we never get a 0 here. So for numerical reasons, we take 1 minus x1 in order to avoid numerical cancellations.
And why do you use cosine and sine? Because if you just take one random variable uniformly distributed and use square root of -2 logarithm of that, I think you would also get that probability distribution, no?
Okay, so what we didn't say here, so this phi is a complex number, so you need two random numbers. You need to have the complex Gaussian distribution. Yeah. All right. So this is the way to obtain normal from normal distribution from uniform distribution, and we will do this at the beginning of each Monte Carlo trajectory. Then in the step 2, we've discussed this briefly towards the end of the lecture yesterday. So there were some questions related to the fact how can we make sure that our molecular dynamics evolutions preserves the measure of the integration. And I will give you an example today of an integrator, the simplest integrator, which satisfies all the necessary conditions in order for it to be the so-called symplectic integrator. So but before introducing this integrator, let me just mention that it's sometimes advantageous to split the Hamiltonian. So before performing molecular dynamics evolution, we will also see in lattice QCD simulations that it's even more advantageous to do so. So since simulations of scalar field theories, in particular in lower dimensions, are not computationally as expensive as simulations of full lattice gauge theories, including the dynamics of the Fermion fields. This is not a crucial step if you want to simulate scalar field theories on the lattice, but it will turn out to be very important strategy if one wants to simulate full QCD on the lattice. But just to explain it on this example of scalar field theories, so let's say that we split our Hamiltonian into the part H1, which depends on the momentum field. So let's call this part H1, and part of the Hamiltonian which we will call H2, which only in this case depends on the scalar field. So H2 would be equal to the discretized scalar field theory action. So this molecular dynamics evolution in case of Hamiltonian split in these two parts would consist of repeating these two steps. So we would split our trajectory length into n sub-intervals. So if this is the beginning of our Monte Carlo trajectory, where we said that we have field configuration phi1 and the momenta phi1, and then at the end of the Monte Carlo trajectory, so this is in Monte Carlo time, some length tau, and we have at the end of the trajectory phi2, pi2. So we will integrate our molecular dynamics equations, so the Hamiltonian equations of motion, by splitting this trajectory into n sub-intervals of a length of the opposite, so epsilon equals to tau divided by n, all right? And for each of these sub-intervals, we would perform the following update. So our field phi and our momentum pi will be updated. So in each of the two sub-steps, we will update one of the two variables. So in the first step, which we will denote I1 of epsilon, pi, so the momenta will remain intact, but the field variables will be updated by some expression, which we will later define as Monte Carlo forces. So this will be the derivative of the first part of the Hamiltonian, which depends on pi with respect to momenta pi. So H1, which is the only part which depends on pi. And then in the second step, we will keep the field intact, but we will update the momenta accordingly, according to the Hamiltonian equation of motion, which corresponds to the momentum pi. So the derivative with respect to pi of the second part of the Hamiltonian, which depends on phi, and the field phi in this step remains intact. Okay, so this it turns out that one can choose to update these fields in any way one wants, as long as so one can choose these sub-intervals epsilon. They don't necessarily have to be equal in each update of momenta and update of phi, as long as in total they add up to the total trajectory length tau. So in principle, one could also have an index I and an index j here, I and j, for the length of these sub-intervals, as long as all of them add to the total trajectory length tau. And the simplest example which fulfills these conditions and allows for the integration of molecular dynamics equations is the so-called Leapfrog integrator. And the choice for a single update of both fields phi and fields, so the momenta and the scalar fields phi in this integrator is chosen as following. So a single update for the subinterval epsilon would be further split into a combination of updates I1 and I2, one updating only the field, the second one updating only the momenta, in the following way. So we will first perform the update of the field for half of this subinterval of the length epsilon. Then one performs the update of the momenta for the full interval, and then one performs further update of the fields for another half of the interval. So basically, then the total trajectory length tau would require this step of I epsilon to be performed n times. So why is it called Leapfrog? If we illustrate on the example of the trajectory of length tau, how does this update really look? So let's take the simple case when our n is equal to 2. So our epsilon would be tau half. Imagine that we only have 2 steps in which we integrate molecular dynamics equations. Often, especially with the Leapfrog integrator, one requires more. But just for the illustrational purposes, so we would first update in the first step, we would have the field update, which would just bring us to the epsilon half. Then in the next step, one would have to update the momenta all the way for the step of a length epsilon. So this would be I2. And then only after that, one would perform a second update of a momenta. So if we want to show the time order of these updates, one would first perform I1, then I2, and then again I1 on the trajectory of the length, on the step of the update step of the length epsilon half, and so on. So as we said, in principle, any choice of any order of these steps is allowed as long as they all add up afterwards to the trajectory of the length tau. So again, first the fields in the next sub update. So in the next sub step, the fields will be updated for half of the trajectory. Then we would update momenta for the whole step epsilon, and only then we would have an update of the fields for another half of the step. So what's particularly important for the choice of the integrator, as we already mentioned yesterday, is the fact that the integration measure in the path integral is preserved. So basically that we had in the path integral, so in the augmented partition function, we had the integration over the momenta, and the integration over the field variables, and the integrators which preserve this integration measure are known as area preserving. And yes.
Why do we here we have plus epsilon and here we have
minus? Yeah. Okay. I'm gonna discuss this in a second, but this is from the fact momenta and the fields are updated in Hamilton equations. So if we go back, if you go back to what we had yesterday, so the update of the momenta and if you recall, the update of the momenta and the update of the fields have the opposite sign on the right-hand side of the Hamilton's equations. But it's good that you mentioned this now, because I just wanted to introduce new terminology. So basically, usually these terms for which we update or we augment the field and the momenta are also known as molecular dynamics forces, again in the analogy with classical mechanics. So we had that, so in the classical mechanics, if you would have an action and then the derivative of the action with respect to the coordinate would be equal to the force. So we will call this first, actually this H2 is the action. So this second term we would call the force term corresponding to the field phi of x. So this would be the derivative of our, so H2 is our discretized action that we've written down yesterday on the board, so S of phi. And if you go back to the discretized version of the action, you can see that when you perform the derivative of the action with respect to phi, you will get the following expression. So you will get the kappa, the hopping parameter, which we've introduced. Mu goes from 1 to 4 in a 4-dimensional scalar field theory. X plus mu hat minus phi of x minus mu hat, which comes from discretizing the derivatives, the covariant derivatives in our action, plus phi of x, 2 times phi of x, plus, and then the derivative of the quartic term with respect to phi of x will give us 4 lambda times phi x squared minus 1 times another phi of x. And on the other hand, the force corresponding to the momentum is much simpler to compute. So since our momentum dependent part is only phi I squared divided by 2, so the force corresponding to the momenta will be the derivative of H1 of pi with respect to pi, and this only gives us, so the derivative of pi I squared divided by 2 with respect to pi I actually only gives us pi I. Okay, so the name for these derivatives is actually molecular dynamic forces. Again, those are not real forces in our quantum field theory, but those are like we have the fictive Monte Carlo time. Those are also forces associated to our artificially created classical mechanics system used for the update of field, used in order to update the gauge configurations and to generate the Monte Carlo, to generate the Markov chain on which we are going to evaluate our observables in a way that we've demonstrated yesterday. So this integrator that we've discussed here, the Leapfrog integrator. So other than being area preserving, it's also symmetric under the time reversal. So this means that, so as we've said earlier, there is always some error associated to the numerical integration. However, since this procedure is symmetric under time reversal, then other epsilon errors cancel. And then the leading error in this integrator is proportional to order epsilon squared, where epsilon is our trajectory divided by the number of updates of this kind that we perform in a single Monte Carlo trajectory. So this is the leading error of the Leapfrog integrator.
So how
Yes.
can you see that the measure is conserved?
How can you see that the measure is conserved? So the time reversal you can see fairly easily if you just
In one way is if you just take the matrix of transformation.
exactly. So you the Jacobian and the measure. Yeah, exactly. So thank you. So so if you write down the Jacobian for the change of the of both of the coordinates, the determinant of the Jacobian has to be equal to 1. Yeah.
If the error cancellation is coming from the time reversal symmetry, then
Yeah.
what is the benefit from the area preserving transformation?
The error cancellation. Sorry, could you
Error
please
cancellation is coming from time reversal symmetry.
exactly.
And what is the benefit from the area preserving?
Preserving. So, so your integrator has to satisfy both in order for you to be able to perform. In order for these 3 steps to actually give you the configurations distributed to the distributed according to the original Boltzmann weight that we wanted to have, so e to the minus s of f. And you will see in a moment what would happen if we wouldn't have if we wouldn't have area preserving integrators. So this is precisely my next example. So so the conservation of the phase space measure, why is it important? So we've said that in this last step we compute e to the minus delta h, and this is an answer to one of the questions also which we had yesterday. So so we said that we want to preserve the measure, and what does this mean actually? So let's assume that our observable that we are trying to the observable that we are trying to estimate in our approach, which uses this augmented partition function which we had yesterday. So instead of integrating only over phi, we've introduced integration over the momenta. So our partition function now looks as integration over the this auxiliary momenta function times d phi times e to the minus now our Hamiltonian, which is a function of phi and f. And if we now want to estimate the expectation value of e to the minus delta h, this would be equal to 1 over the partition function, as we've seen yesterday, times integral d phi, so integrating over both of these variables, times e to the minus our original Hamiltonian. So this is the Boltzmann weight, and we said we are estimating the observables by multiplying them with the Boltzmann weight, integrating over pi and phi, and dividing by the partition function. So we still need to multiply with an actual observable that we are trying to estimate. So this would be e to the minus delta h of pi and phi. Okay, so this is our observable, and we've seen yesterday that in the path integral formalism, you would estimate. So after we've augmented our partition function with these auxiliary variables pi, then we have then our new partition function is integrated over pi, and our Boltzmann weight becomes e to the minus h, but the averages of the estimators of the observables do not change, and they are still distributed with respect, they correspond to the original path integral, which only has e to the minus and then the Euclidean action in the exponent here. So all right, so assuming that we have the conservation of the phase space measure, so that this equals to 1 over z, and then if we change from some variable pi and phi to d pi prime, d phi prime, and then we can evaluate this exponent here. So, so if delta h equals to pi prime minus phi prime if these are the momenta. So the Hamiltonian evaluated at pi prime high prime if these are the momenta at the end of the trajectory. Let me write this down a bit more clearly. So so say that pi prime and phi prime are the momenta and the field configuration at the end of the trajectory, minus integrated with a certain integrator which is area preserving, minus the Hamiltonian at the initial momenta and the initial field configuration. Then here in the exponent, this term will cancel, and we will only have e to the minus Hamiltonian of phi prime, where, as you can see, this is, if we perform the change of variables, this is nothing but the original definition of our partition function. So this is z divided by z, and we get 1. Okay, so so this is so if the integrator is area preserving, then an expectation value of e to the minus delta h is equal to 1. And combined with this condition here that we have in the hybrid Monte Carlo algorithm, this actually ensures that that we are drawing our samples from the correct distribution, which is proportional to this Boltzmann weight of e to the minus s. So without, and this also answers another question which we had yesterday, possibly. So so what happens if r delta h is really large? So in principle, so since average of e to the minus delta h has to always be 1, so if you have, say, large negative value of the delta h, or yeah, so it would take a lot of, so the algorithm would make sure that you would have to have a lot of values with the opposite of the delta h in order to compensate and to average over your Monte Carlo chain over your Markov chain to actually get this average of 1. And then finally, a little bit more on the step 3 of the accept reject step. So the accept reject step is there in order to correct for the error that we are making in the step 2. So the error is proportional to the simplest integrator. As long as it's time reversal, it's proportional to epsilon squared. Then there are some more advanced integrators which would either reduce the prefactor in front of this order a squared. These go under the name of, so all of the integrators which have order a squared go under the name of the second order integrators. And then one can also construct higher order integrators where one would have an error of higher powers of epsilon. If we have time reversal, then it would be order of epsilon to the power of 4. So these allow us to integrate molecular dynamic equations with higher precision. However, the toll is usually that they are numerically more expensive in our computer simulations. And in any case, since it's impossible to integrate numerically molecular dynamics, so to perform this molecular dynamics evolution exactly, we said that we need to correct for this error in the integration with the accept reject step. And how is this accept reject step performed in practice? So if we have our initial Hamiltonian with field value, okay, we've been writing momentum first, so with the momentum phi1 and field phi1, and then after the molecular dynamics update, we have our final Hamiltonian with phi2 momenta and phi2 momenta. And we said that we want to implement this last step with the acceptance which corresponds to the minimum between 1 and e to the minus delta h. In practice, this probability for acceptance is implemented in the following way. And if you've done if you've done Monte Carlo simulations of spin systems, you've probably seen this. If not, in any case, let me remind you or tell you how it's done. So in practice, in order to obtain the probability where e to the minus delta h is evaluated and accepted, so we can see that if delta h is smaller than 0, then e to the minus delta h is always going to be e to the minus delta h is always going to be larger than 1. So in this case, we know that we should immediately accept the configuration. And in our computer program, when we compute the delta h as h of phi2 f2 minus h of phi1 f1, then if delta h is larger than 0, in order to have this acceptance rate, we have to throw another random variable r. So we're using random numbers in the first step in order to generate the momenta with a monetary distribution. And here we just throw one random number in the range again from 0 to 1. And we accept if e to the minus delta h is larger than this random number r, and reject otherwise. So if e to the minus delta h is smaller or equal to r. So this is how this accept reject step is implemented in the numerical simulation. And this concludes the discussion of the application of hybrid Monte Carlo algorithm on this simple example of scalar field theories. Let me just mention that there are simple ways to simulate scalar field theories. I've discussed this algorithm here because, as we will mention and as we will see actually tomorrow, this is the only algorithm which can efficiently currently simulate fermions, fermion fields, which are part of the QCD action. Otherwise, there are cheaper and simpler ways and more efficient ones in a sense of the autocorrelation time that we mentioned yesterday. So there are more efficient ways to, if you want to simulate only scalar field theories, you don't have to do hybrid Monte Carlo. You can actually do something very similar to only this first step, the heat bath algorithm. So you don't need to augment your partition function with a momentum field, and you don't have to perform the integration of these molecular dynamics equations. But this was a nice toy model to discuss hybrid Monte Carlo. And as we will see, things get a little bit more complicated once these field variables are changed for the gauge field variables, and once this action also depends on the fermionic fields in the QCD of the QCD action. So, but the basic idea remains the same, as we will see tomorrow. Any questions related to this? Yes.
I've got a question. The Leapfrog integrator is an explicit integration scheme for a differential equation. Is there also, or do you know of any integration scheme that is, or could be applied that is implicit with regard to better numerical stability?
So what do you have in mind by implicit integrators? If you give me the
Integrators have the property that if you have like a differential equation of the form y prime is equal to f of y,
yeah.
something like that. Explicit integrators have the property that the next step that you calculate only depends on the old result. So the new result for the next step can explicitly be written as the former time step. For implicit integrators, you have a dependency on both sides of this equation on the new time step. So you can't explicitly solve them by hand, but you actually have to run some kind of what is it called? Yeah, exactly.
Well, so the way to actually, so there is this. So, for example, there are integrators which move forward and backward in time, but this would still be explicit, even though you would. So, for example, the way to. So, I'm not aware of any like implicit in the way that you define it.
Well, usually the general advantage is that you can safely have a larger step size, right? Because you don't suffer that strongly from.
So the integrator she wrote here, you have to use a relatively small step size, but there are fourth order integrators
Where you can, yes.
where you can use a relatively large step size that is
So, for example, one can explicitly cancel this higher order integration by, well, having a little bit more complicated integration scheme. So, for example, this O'Millian integration scheme would, you can change the coefficient in front of this just by playing with the lengths of these updates, so having uneven updates, and you can see that by writing basically the difference between your actual, so the actual Hamiltonian and the actual Hamiltonian of the theory and the Hamiltonian that you are simulating here numerically, and then canceling these higher order terms explicitly. So first of all, yeah. Again, the length of the step actually determines the coefficient in front of this here, but then adding some additional terms in the integration, so more complicated updates here would in principle cancel this order a squared terms. So in that case, it is a bit more complicated because you're going back and forward, but it's still explicit. And for all purposes, actually, this order, fourth order integrators are very, very give very small violations of the trajectory at the end, but they're just a little bit more expensive to apply, but still don't require any solving. So if I understand you correctly, what do you mean by implicit? You would require to solve your inverse problem during the trajectory somewhere. And this sounds to be more expensive than the implementation of this fourth order integrator. Maybe it can be tested in some simpler theories, but for QCD, the advantage of these integrators is that you don't have to additionally invert your problem. All right, and finally, let's discuss quantum chromodynamics on the lattice. So now that we've learned in much detail how to discretize scalar field theories and how to simulate it, we can move on and discuss how to discretize fermion fields and gauge fields, and how to represent them on the lattice. So before writing down, I will first start with discretizing the fermion action, and then move to the discretized version of the gauge part of the QCD action. But before going there, let me just remind you of some basic properties of QCD, which you probably know already. So you know that in QCD we have gauge potential, which we will denote as a mu of x, which are elements of the SU3 algebra, so the Lie algebra corresponding to the SU3 gauge group. So these represent the gluon fields, and recall that each SUN algebra element are actually traceless Hermitian matrices. So a mu dagger equals to minus a mu, and the trace of a mu equals to 0. And then let's look at the gauge transformation of both gauge fields and the matter fields in QCD. And as we said, when we are discretizing theory and the lattice, we try to preserve all the important properties of the continuum theory in order to be able to perform the continuum limits. So the symmetries will be preserved as much as possible. Of course, I mean, by changing from the continuum space-time to the discretized lattice. So we will naturally, as we've discussed for the scalar field theory, we will naturally break parts of our Lorentz transformations, but such an important quantity as gauge symmetry is something which we definitely want to preserve when defining our theory on the lattice. And as you know, under gauge transformation omega of x, the gauge fields A mu transform as omega of x, A mu of x, omega inverse, plus, since we have non-abelian fields, we also have this term, omega of x, d mu omega x minus 1. And at the same time, matter fields under the same SUN transformation, the matter fields transform as phi of x prime. So in the fundamental representation, we would just have omega of x, phi of x. So, and then a third important thing, if you want to preserve gauge invariance, is also to have the, so since the fermionic part of the QCD action, as you know, has covariant derivatives, we would also want to make sure that the gauge transformation of the covariant derivatives is also implemented on the lattice. So the covariant derivative is there in the Euclidean space-time. There is no I, so we would have just d mu plus a mu of x psi of x, if psi denotes some matter field, and then d mu prime, so the gauge transformation of the covariant derivative would just be omega of x d mu psi of x, and that's why we call it the covariant derivative. And if we want to write down the Fermion action on the if I want to write down the Fermion action on the lattice, we would just have to discretize the covariant derivative. So similarly to the discretization of the scalar field theory on the lattice, we've placed the natural geometrical way to do it was to place scalar field variables as dynamical variables on the sides of the lattice, and we will do the same here. So our quark fields in QCD will be associated to the sides of the lattice and defined at each discrete lattice point x. And we will start from the classical Euclidean action in continuum. So similarly as for scalar field theories, we can write down the QCD action in Euclidean spacetime, where d slash is the covariant derivative plus m 0 phi of x. And we won't write down, we mainly won't write down unless when it's necessary, the Dirac so Dirac and color indices, but in this case, let me just write down. So the gauge index group will be denoted with ij and j here, and then we also have Dirac spinor indices, which will be silently assumed towards the end of these lectures. So if psi bar has an index alpha, then the Dirac matrix has Dirac spinor indexes alpha beta, and beta is the Dirac spinor index of psi of x. So let's look in a little bit more detail into this Dirac matrix of the Fermion part of the QCD action. So gauge group index, Dirac index. So as we know, this covariant derivative equals to the gamma mu d mu plus the gauge field. And in the Euclidean space-time, we will have gamma mu multiplying the covariant derivative d mu delta ij plus a mu ij again, group indices, and plus m0, which is diagonal both in the Dirac and group indices. And these matrices are a little bit different from the gamma matrices you're used to in the Minkowski. So these are Euclidean Dirac gamma matrices. So they act on Dirac indices as well, but the definition is slightly different than in the Minkowski. So I'm going to write down here for what is the convention that we are using in these lectures, and it's also most commonly used convention for the Euclidean Dirac matrices. So these 2 by 2 matrices, so it's a 4 by 4 matrix acting on Dirac indices, and these 2 by 2 matrices are defined as following. So E4, which is our time coordinate, as we know in the Euclidean, is a unit 2 by 2 matrix. So 1, 0, 0, 1. And EK are the standard Pauli matrices. So K goes 1, 2, and 3. And for Dirac matrices, the usual relations hold. So these are Hermitian matrices, and the commutator of the two Euclidean gamma matrices equals to the 2 delta mu nu. Another important point is that the Euclidean gamma 5 matrix is slightly different from the Minkowski gamma 5. So the Euclidean gamma 5 is equal to gamma 1 times gamma 2 times gamma 3. So these are matrices corresponding to the spatial directions, times gamma 4, defined, as you can see here, with this unitary matrices on this two fields. So basically, so this is the definition of gamma 5, and gamma 5 is such that, so it's as well as the original Euclidean gamma matrices, so gamma 5 is also Hermitian matrix, and gamma 5 squared gives 1. And so in order to separate the topics related to the discretization of gauge fields and the discretization of fermion fields, let us first look at the free fermion action. So we will for now neglect the interaction term and write down the free fermion action in the continuum. So we have d4x, phi of x, gamma mu, d mu, this first term of the Dirac matrix, plus m0. Okay, so let's split the two terms. Just the integration is over all of them. Psi bar of x. So this is the only term remaining from the covariant derivative part. And we will have m0 psi bar of x psi of x. So as we did in the first lecture on scalar fields, we will look again at the representation which tells us about the particle content of the theory, so which relates the two-point function, the spatial two-point function, and the spectrum of the theory. Thanks to the Swedish people in the audience, I've learned that the right way to pronounce this is Kjellin-Lehmann, correct? Good. All right. So from now on, we're going to call it Kjellin-Lehmann representation of the two-point correlator. So we are looking into the two-point function of in the free fermion case. In Euclidean space-time, And for positive time coordinate. And it turns out that following similar derivation as we had for the scalar field theories, we don't have time to go over all the steps here, is that we get the following expression for the two-point field correlator. So the integration over the spatial momenta times 2 energy of the particular state n, so it's sum over all multi-particle states, multiplying e to the minus en of p times time coordinate x4 plus I vector p vector x multiplied by I phi slash plus mn and some normalization factor zn squared, where we will call this the momentum in time direction is equal to I times vector pi squared plus mn squared. We've said that this mn is the mass at the so the energy at the center of mass frame. So this equals to I times this En of P, and we will in the following sometimes call this omega of P. So we've seen in the scalar theory that the spectrum contains a single particle state with some energy En of P. And we will use this to study also the particle content of the discretized fermionic theory on the lattice and draw some conclusions about what is the best way to discretize the theory on the lattice. So the simplest and naive way to discretize this fermionic part of the QCD action without the so in the free theory would be just to replace again the derivatives, the continuum derivatives, with finite differences. So this we've learned already in the scalar field theory that we can do. So we'll just replace the mu with 1/2 of the forward plus backward derivative. So we've said that this symmetric derivative has faster convergence to the continuum limit than each of these derivatives individually. And each of these derivatives just looks at the nearest neighbor differences, so between the field phi x, and if this is a mu direction, then this nearest neighbor would be phi of x plus mu hat times the lattice spacing A. So if we discretized the continuum, we replace the continuum space-time with a discrete lattice, then instead of the integral, we've seen the prescription tells us that we get the sum over all the lattice points. The fermion fields are already defined in each of the lattice points, and the derivatives are replaced with finite differences, and we get our first attempt. So the expression, which is the first attempt to discretize fermion action, would be the following. So 1/2 of d mu plus d mu star, so the symmetric derivative, times gamma mu times psi of x, and plus the mass term, which looks the same as on the right-hand side in the continuum. And in order to, again, understand what is the relation between the two-point function and the spectrum of the theory, but also to see whether this discretization of the fermion action makes sense, we will look at the propagator in the Schelin-Lehmann representation. So the propagator in Schelin-Lehmann representation will be the following. So we will have sum over all mu I, some rescaled momentum variables. I will write down in a moment how they look, plus m0 times 2 pi to the power of 4 and times the delta pi plus q. So the propagator in momentum space turns out to be the following, where this pi mu is defined as 1 over a sine of the original momenta multiplied by the lattice spacing. So we have skipped some algebraic manipulations in order to get here, but the whole procedure to obtain this is very similar to the one which we had in the scalar field theories. And in order to understand what is the so we've said also that the exponential decay of the two-point function, as was also mentioned in the discussions yesterday with Guy, so we've said that the exponential decay of the spatial two-point function, so of the two-point function in the position space, actually depends on the poles of the propagator defined by this Schelin-Lehmann representation. And in order to understand this decay in the position space of the two-point function, we will first need to compute the two-point function in the momentum space, which will be the inverse of the propagator in this Schelin-Lehmann representation. And we will then perform Fourier transform and go back to the initial two-point function in the position space. So skipping again, some rather simple manipulations which one needs in order to perform in order to obtain the inverse of the propagator. But I'm going to give you some hints if you want to repeat this, if you want to perform this calculation on your own. So there is a useful identity which holds for regular gamma matrices and can be also derived for the Euclidean gamma matrices as well. So if we have unity multiplying some constant A plus, which will be this mass here, mass term here, plus I times sum over all directions of gamma mu B mu, which will be our gamma mu and pi mu tilde here. So there is a tilde here missing. So the definition of this pi mu tilde is the following: 1 over A sine A times pi mu. So if we want to invert this expression, which is precisely how we're going to get the inverse of this propagator in Shalane-Lehmann representation, so it turns out that the inverse of this expression, so using the properties of the gamma matrices, which were written here earlier, you can demonstrate that the following holds, and then use it to invert the propagator. So A squared plus sum over mu B mu squared, and you have A times unity matrix in the numerator, minus sign now I times the original sum over mu gamma mu B mu. And that's why in the expressions which will follow, you will actually see m0 squared plus sum over mu and then pi mu tilde squared. So we will have a lot of sine squared of A pi mu in the expressions which follow. So after performing this inversion, obtaining the two-point function in momentum space and performing a Fourier transform to obtain a two-point function in position space in Shalane-Lehmann representation, one gets the following expression, and we can read off directly from this expression the particle content of our discretized free fermionic theory. E to the minus I pi x minus omega p x4. We said we'll call omega this energy in the time direction, so the time component of the momenta, divided by sine hyperbolicus of 2 times the energy in lattice units times, and then a rather lengthy expression for which I'm going to use the whole next row. Gamma 4 sine hyperbolicus omega p a minus I times sum over k, so a term like this, which we obtain after inverting the propagator. gamma k sine pk a plus m0 a plus, I will use another row, minus 1. So this is a term corresponding to the spatial component, minus 1 x4 divided by a minus gamma 4 sine hyperbolicus of omega of p. So the energy times a minus I times sum over all spatial gamma matrices multiplied by sine pka plus m0 a. So I will close this bracket here, and finally, so this is all under the integral, and it looks a little bit more complicated than the propagator in the continuum theory, but in principle it tells us that it can tell us several things about the particle content of our discretized fermionic action. So the first thing it tells us is that two terms in this sum actually correspond to the same energy, but different residues if one would look at the poles of this propagator in the pi4 plane, in the plane corresponding to the time momenta. And we get this in each of the directions, so each of the spatial and time direction. So basically, this function omega of p, which tells us how many multi-particle states do we have in our propagator, it actually it tells us that this function actually has, so the spatial, the function which depends on the spatial momenta has 2 to the 3 minima inside the first Brillouin zone. So we've said that on the lattice, our momenta are limited to the first Brillouin zone. So, but even in the first Brillouin zone, when we've discretized our Fermion action in this way, we have the choice of some rescaled momenta pk bar to be equal to nk times pi over a. So we said again that our a times p on the lattice has to be smaller than pi. So in order to remain in the first Brillouin zone, but however here the momenta that are allowed, so we can have this nk being equal to either 0 or 1. So basically for each k we can have either momentum 0 or either pi over a, and each of them gives us poles in this Shalin-Lehmann expression for the 2-point function. there is, so we can expand this 2-point function around this minima of the energy function, and we can continue this discussion in a bit more detail tomorrow, but let me just tell you what the main conclusion will be after because we are running out of time already, but it will turn out that basically there are two contributions here in the energy, so in the time direction, in addition to the multiplying this 2 to the 3 minima inside the first Brillouin zone. And so by introducing such a discretization of the Fermion action, we will discover from the Gillian-Lehman representation of the 2-point function, which actually tells us about the particle content of the theory. It will turn out that this theory represents 16 particles with equivalent mass. So basically, there are 16 different fermions which are represented with such a discretization of the Fermion action, and this is known as Fermion doubling problem. So we've started with a theory which has only one relativistic particle, and by discretizing it in such a way, we will end up with a theory which has 16 relativistic, which describes 16 relativistic particles, which we call Fermion doublers. And we will discuss in a little bit more detail tomorrow how do we overcome this problem and define a discretized version of the Fermion part of the QCD action, which does not have these unwanted doublers. Thank you.